I want you to picture something for a second. Next time you hold your smartphone, or the next time you see a really sleek new electric vehicle just silently gliding down the street.
Or even looking up at a massive wind turbine on a hill, right?
Exactly, yeah. When you see those things, I want you to really think about what you are actually looking at. Because on the surface, what you see is sleek design. You see the magic of software.
You see the clean future.
Right. You're looking at the vanguard of this pristine, zero-emission future we've all been promised. But if you peel back that digital curtain, if you scratch beneath that incredibly smooth, futuristic surface, you find something completely different.
Something very messy.
Very messy, highly toxic, and highly concentrated. These modern miracles are anchored to the physical world by a hidden industrial reality. We think we live in an era of wireless software and cloud computing, but the reality is our clean future requires some of the dirtiest heavy industry on the entire planet.
It's a profound disconnect, honestly. I mean, advanced Western economies have spent the last few decades falling just deeply in love with the digital world.
Oh, absolutely.
We celebrate apps, we celebrate finance, the user interface. We've basically convinced ourselves that the physical world is somehow obsolete or, at least secondary.
Like it doesn't matter anymore.
Right. But a drone is not just software. An electric vehicle is not just an app on wheels. They are material systems. And if you want to understand geopolitics today or the physical constraints of clean energy and aerospace, you have to stop looking at the software and start looking at the periodic table.
Which brings us to the core of what we are doing here today in this deep dive. We are looking at a very specific slice of that periodic table, 17 elements known as the rare earths.
The famous 17?
Yeah. And just to clear the air for you listening right now, we aren't going to spend the next hour drumming up panic about global dominance or, repeating breathless cable news headlines.
We've all heard enough of those.
Exactly. This is about uncovering a fundamental truth about how the physical world actually works. Because modern geopolitical and economic power doesn't belong to whoever just happens to have the right rocks sitting in their borders.
No, it belongs to whoever can conquer the incredibly difficult, almost punishing chemistry required to turn those rocks into reliable components.
We're so accustomed to thinking of natural resources the way we think of oil or gold, right? You find the deposit, you extract it, and boom, the hardest part is done.
Right, extraction is usually the main hurdle. But with rare earth elements, getting the rock out of the ground it's barely the prologue.
Just the beginning.
Yeah, the real story, the place where fortunes are made and national security is secured or lost, is the massive industrial gauntlet that follows the mining.
So I want to start with the name itself, because right out of the gate, the term rare earths has to be one of the worst pieces of branding in the history of science.
Oh, it's a massive misdirection.
Right. I mean, when people hear the word rare, they naturally equate it with precious metals, gold, platinum, rhodium.
Elements that are genuinely scarce in the Earth's crust, yeah.
Elements where humans can only find tiny, isolated flakes of them.
But rare earths are not rare in that ordinary geological sense at all. Some of these elements are actually more abundant in the Earth's crust than copper or lead.
Wait, pause right there. We use copper for seemingly everything. I mean, every wire in your house, the plumbing, the entire electrical grid. And you're saying some of these supposedly rare elements are more common than copper.
By orders of magnitude in some cases, yeah. Cerium, for instance, which is the most common rare earth, is geologically ubiquitous.
It's everywhere.
Everywhere. Even neodymium, which we are going to talk about a lot because basically the beating heart of the modern economy, is not scarce in the way the word rare suggests.
I was actually looking at this quote in our sources from Julie Klinger. She's a geographer who wrote a foundational book on this rare earth frontiers.
Oh, yeah, brilliant book.
Yeah, and she was speaking at a public event and put it so plainly. She said, rare earths are everywhere. They are not rare. You could go dig on the banks of the Charles River and you'd probably find some traces of them.
That's completely true.
I love that imagery because it instantly breaks the spell, If I can take a bucket down to the mud of the Charles River and scoop up rare earths, what is the actual problem here? Why are we freaking out about supply chains?
Well, the problem is that while nature manufactured plenty of rare earth atoms, nature did not do us the favor of concentrating them in convenient places.
Ah, so they're spread out.
They are highly dispersed. You might find traces in the Charles River, but you can't build a commercial mine to extract one atom at a time. And worse, from an engineering perspective, when you do find a concentration of them, they almost always occur together.
Right, nature bundles them up.
Exactly. And chemically, they are almost identical to one another.
I've seen them described as a family of siblings who all look completely identical, dress exactly the same, and just refuse to let go of each other's hands no matter how hard you pull.
That is a perfect analogy. The scientific reason for that sibling resemblance is something called the lanthanide
The
contraction.
lanthanide contraction. Okay, what is that?
So, without getting too bogged down in a chemistry lecture, these elements fill their electron shells in a very unusual way. As you move across the periodic table, they get heavier, but their physical size, their atomic radius, actually shrinks slightly.
Wait, they get heavier but smaller.
Yeah, which means they all end up having very similar ionic sizes and chemical properties. So because they behave the same chemically, the Earth's geological processes don't sort them out. When magma cools or water dissolves minerals, they precipitate together.
So they're tightly bound together in the rock.
Very tight. And to complicate matters further, they frequently crystallize in minerals that also enthusiastically bond with radioactive elements.
Like thorium and uranium.
Exactly. So if
Yeah.
you want to mine rare earths, you aren't just digging up dirt. You're engaging in incredibly difficult chemistry to separate identical twins. You are managing highly unpleasant chemical waste, and you're dealing with radioactive byproducts all at the same time.
Sounds like a nightmare.
It is. You end up with a category of materials that are geologically everywhere, but industrially agonizing to produce.
Let me make sure I'm mapping this correctly to the political conversation, because when politicians get on television during some trade dispute and confidently demand to know, like, does the U.S. have rare earths in the ground? They are fundamentally misunderstanding the crisis, aren't they?
They are asking a question that was solved decades ago. Yes, the United States has rare earths in the ground.
We have the rocks.
We have the rocks, but having the rock does not grant you strategic power. The real question, the one that actually matters for national security, is whether the U.S. has them in the right minerals at a high enough grade with a viable legal permitting path.
And the processing capacity. Right.
Huge processing capacity. You need the chemical separation plants, the environmental controls to handle the toxic and radioactive waste, and a downstream manufacturing base to actually turn them into components.
Okay, let's unpack this with an analogy. It's like the difference between finding sugar dissolved in a cup of coffee versus finding a solid sugar cube.
Okay, I like where this is going.
Right. If I ask you if sugar is rare, you'd say no. But what if the only way to get your sugar was to recover a single tablespoon of it that someone had completely dissolved into an Olympic-sized swimming pool?
A swimming pool filled with mud.
Filled with mud and toxic waste. Finding a pure sugar cube is like finding a vein of gold. What we have to do with rare earths is build a massive billion-dollar chemical filtration plant just to coax that single tablespoon of sugar back out of the toxic mud.
That completely captures the sheer physical scale of the processing. I mean, you have a massive volume of raw material that you have to drill, blast, haul, crush, and bathe in harsh acids just to extract a tiny fractional percentage of actual value.
So let's actually name the players in this muddy pool so we know who we are dealing with. The sources define the rare earths as a group of 17 specific elements.
Right, the 15 lanthanides plus 2 others.
Yeah, the lanthanides. For anyone trying to picture the periodic table from high school chemistry, it's that long, detached row floating at the very bottom, running from lanthanum to lutetium. And then geologists add scandium and yttrium to the mix.
Yeah, scandium and yttrium aren't technically lanthanides by atomic number, but their geochemical behavior is so similar that they are universally grouped together by the industry.
Now, I know that rattling off names like praseodymium, promethium, samarium, europium, it sounds like a lot of dense academic jargon.
It sounds like elements you'd use to power a starship in a sci-fi movie.
It really does. But the crucial takeaway from our sources is that we cannot talk about rare earths as if it's one monolithic market. It is a diverse family.
Exactly. Each of these 17 elements has completely different industrial applications, wildly different market values, and entirely different levels of strategic urgency.
Our sources draw a very sharp, very important line here between what they call the light rare earths and the heavy rare earths.
And that distinction unlocks the entire geopolitical puzzle. The light rare earths, which include elements like lanthanum, cerium, praseodymium, and neodymium, are generally much more common.
So when you find a deposit, it's mostly these lights.
Yeah, the vast majority of the volume will be these light elements.
And the heavy rare earths, elements like dysprosium, terbium, and holmium.
The heavies are significantly less abundant. They often form in entirely different types of geological deposits, which are much harder to find in economically viable concentrations, and they are incredibly difficult for the U.S. and its allies to secure outside of China.
So if an exploration company puts out an excited press release claiming they've discovered a massive new rare earth deposit somewhere in the American West, we shouldn't just applaud and assume the crisis is solved.
Definitely not. You have to look closely and ask, which exact rare earths did you find?
Right, because if they just found a mountain of cerium and lanthanum, which are abundant and cheap, that might be a nice mining project. But it does absolutely nothing to solve the strategic shortage of heavy rare earths like dysprosium.
Exactly. A mine that produces only light rare earth concentrate does not fix a national security vulnerability regarding heavy rare earths. You have to scrutinize the elemental breakdown.
Which naturally leads us to the massive why of it all. If these elements are such an absolute nightmare to extract from our toxic swimming pool, why do we bother? What makes them worth billions of dollars in international trade wars?
Magnets.
Magnets. The sources are very clear on this. While they're used in petroleum refining and ceramics, magnets are driving the global panic.
Today, the absolute stars of the show, the elements dictating the pace of the global energy transition and modern warfare, are the ones used to engineer high-performance permanent magnets.
Specifically, 4 key elements from our list of 17: neodymium, praseodymium, dysprosium, and terbium.
That is the critical quartet. The U.S. Department of Energy explicitly singled out those 4 elements in a recent critical materials assessment.
They're that important.
Yeah. Their irreplaceable role in the permanent magnets used in EV motors and wind turbine generators makes them the most strategic materials of the 21st century.
Okay, I have to challenge this premise because I think a lot of people had the same mental block I did when I first read this.
Let's hear it.
When I hear the word magnet, I think of the little brittle ceramic rectangle holding up a grocery list on my refrigerator, or maybe a red horseshoe magnet from a cartoon. Why on earth are global superpowers fighting over magnets? Can't engineers just build motors without them?
It's a vital question, because we had electric motors for a century before rare earths became a flashpoint.
Exactly.
But to understand why we can't just go back to the old way, we have to look at what these specific rare earths are doing at a subatomic level. It comes down to the architecture of their electrons.
Oh, so?
Rare earth elements have deeply buried electrons in what chemists call the f orbital.
The orbital.
Think of it as a deeply protected inner layer of the atom. Because these magnetic electrons are tucked away close to the nucleus, they don't get easily scrambled or knocked out of alignment by outside forces.
So they hold their charge better.
Right. When metallurgists mix a rare earth like neodymium with iron and boron, creating a neodymium-iron-boron magnet, the neodymium acts as a microscopic structural framework. It locks the magnetic field of the iron tightly into place.
So it's forcing all the magnetic energy to point in the exact same direction, constantly.
Exactly. It creates an incredibly strong, permanent magnetic field in a very small volume of material. And that fundamentally changes the paradigm of mechanical engineering.
Because a motor's entire purpose is to convert electricity into physical motion.
Or a generator converting motion into electricity, yeah. If you have a wildly powerful permanent magnetic field already sitting inside that motor for free, you don't have to use up extra electricity to create that field.
Because that's how an older induction motor works, right? It doesn't have permanent magnets. It has copper wire coils, and you have to pump electricity into those coils just to generate the magnetic field required to make the motor spin.
Precisely. You're wasting energy just to create the field. But with a rare earth permanent magnet, the magnetic field is just there. It is permanent.
Which must give engineers a ton of freedom.
Immense design freedom. You can radically shrink the size of the motor. You can make it vastly lighter. You increase its torque density, meaning it has incredible immediate turning power, and you vastly improve its electrical efficiency.
Let's apply that to an electric vehicle. You technically can build an EV using an older induction motor that relies purely on copper coils, right? Avoiding rare earths entirely.
Automakers certainly can. Some early EVs did exactly that. But the engineering trade-offs are brutal.
What happens?
Without rare earth permanent magnets, that motor becomes significantly heavier. It takes up much more physical space in the chassis, and it draws more electrical power from the battery just to operate.
So your EV is heavier, slower off the line, and loses a significant amount of driving range.
Exactly. And in today's fiercely competitive automotive market, if you're trying to sell a premium EV, telling the consumer they're losing 30 or 40 miles of range just because your motor is heavy and inefficient,
That's a total deal breaker. The consumer won't buy it.
they won't. The physics of the permanent magnet translates directly into commercial viability. But the stakes get even higher when we look at infrastructure, like modern offshore direct drive wind turbines.
Those colossal structures out in the ocean.
Yeah. Historically, wind turbines used massive, incredibly heavy mechanical gearboxes to step up the slow rotation of the blades into the fast rotation needed for the generator.
And gearboxes are basically just thousands of moving metal parts grinding against each other.
Which means friction, wear and tear, and eventually failure. Now imagine having to constantly send maintenance crews out into the ocean, climbing 400 feet into the air to repair a massive gearbox.
Sounds expensive and dangerous.
Very. But by using a colossal, rare earth permanent magnet generator, engineers can completely eliminate that mechanical gearbox. The blades connect directly to the generator. It dramatically simplifies the machine.
It sheds tons of weight at the top of the tower, too.
Right, and vastly improves reliability over a 25-year lifespan. It's the difference between maintaining a complex mechanical watch and a solid-state visual watch.
Okay, and then we move to the sector where compromise is simply not an option: defense. Our sources emphasize the defense industrial base heavily here. We are talking about precision-guided munitions, advanced radar systems, drone optics, and actuators on fighter jets like the F-35.
And an actuator is effectively just a highly specialized, incredibly precise motor.
Right, but if you're an aerospace engineer designing a fifth-generation fighter jet, your constraints are agonizing. Every single ounce of weight matters.
Every cubic inch of internal space is fought over. You cannot compromise by installing a larger, heavier copper coil induction motor to move the wing flaps. You need the compact, extreme torque that only a rare earth magnet can provide.
The sources quote the Government Accountability Office on this. They noted that the DoD considers these materials essential because they enable unique, high-performance combat capabilities.
Which is the military's polite way of saying, without these magnets, our planes are heavier, slower, and less lethal.
Okay, so that perfectly explains the role of neodymium and praseodymium. They are the light rare earths, and they provide the muscle. They supply the raw, permanent magnetic strength.
Yes, the muscle.
But you mentioned earlier that there are 4 critical elements. Where do the heavy rare earths, dysprosium and terbium, fit into this motor?
That brings us to a major metallurgical hurdle known as the heat problem.
The heat problem.
Electric motors generate heat. Fighter jet engines generate extreme heat. A standard neodymium magnet is incredibly strong when it's sitting on a desk at room temperature. But as it heats up, those electron alignments we talked about earlier start to vibrate and scramble.
Also, they lose their grip.
Yeah, if it gets too hot, it crosses a threshold called the Curie temperature, and it permanently loses its magnetic properties. It literally becomes just a useless, heavy lump of metal.
Which would be catastrophic. Imagine you're in an F-35, you pull into a steep climb, the engine bay temperatures spike, your actuators lose their magnetism, and suddenly you can't move the flaps.
Or, on a civilian level, you're merging onto a highway in an EV in the middle of summer in Arizona, the motor runs too hot, and it just dies.
Just totally unacceptable. So how do they solve it?
To solve the heat problem, metallurgists take that neodymium alloy and they sprinkle in small, highly precise amounts of dysprosium or terbium.
The heavy rare earths.
Right. These heavy rare earths have an even more robust electron structure. When they are integrated into the crystalline lattice of the magnet, they act like thermal anchors.
So they pin the magnetic structure in place.
They pin it down. They act as a heat shield, allowing the neodymium magnet to retain its extreme performance even under demanding thermal and mechanical stress.
So neodymium and praseodymium are the raw muscle, but dysprosium and terbium are the heat shields that allow the muscle to actually survive inside a burning engine.
Precisely. And because dysprosium and terbium are heavy, rare earths, they are much scarcer in nature and exponentially harder to secure from allied supply chains. You only need a tiny fraction of dysprosium by weight in a motor, but that tiny fraction carries an overwhelming amount of strategic leverage.
The mismatch of scale here is just staggering to me. Our sources highlight a Goldman Sachs analysis that estimates the entire global rare earth market at roughly $6 billion.
$6 billion.
In the grand scheme of the global economy, $6 billion is nothing. It's a rounding error. It's tiny compared to the hundreds of billions traded in oil or steel.
It's remarkably small in pure dollar terms.
But that tiny $6 billion stream of raw material is the foundational pillar holding up trillion-dollar downstream industries.
The entire global EV transition, the wind power rollout, defense, electronics.
All of it rests on this incredibly narrow fulcrum of rare earth magnets.
Yeah.
If you interrupt that $6 billion market, the economic and security damage cascading downstream is astronomical.
And that profound asymmetry, the tiny bottlenecks supporting massive systems, is what makes rare earths so incredibly potent as a geopolitical weapon.
Knowing what they do and why the physics make them irreplaceable, let's map this out in the real world. Where are these crucial rocks actually sitting?
Well, geology dictates the starting line. Globally, there are 3 major geological profiles of rare earth minerals that dictate the industry: bastnäsite, monazite, and ion adsorption clays.
Let's start with bastnäsite. What is the physical reality of this mineral?
Bastnäsite is a hard rock mineral. It usually occurs in carbonatite formations, which are basically igneous rocks formed by ancient volcanic activity. It's currently one of the most important sources of light rare earths in the world.
And we actually have a lot of this in the U.S., right?
We do. The famous Mountain Pass mine in California, which is the only major active rare earth mine operating in the U.S. today, is a massive bastnäsite deposit. China also utilizes vast bastnäsite ores at their Bayan Obo megamine in Inner Mongolia.
So if you need lanthanum, cerium, and the muscle magnets, neodymium and praseodymium bastnäsite is a phenomenal resource.
It is, but it comes with a major limitation based on what we just learned.
It lacks the heat shields.
Exactly. Bastnäsite deposits are notoriously poor in heavy rare earths. You cannot extract meaningful commercial quantities of dysprosium or terbium from them.
Okay, mineral profile number 2.
Monazite.
Monazite is a phosphate mineral, often appearing in heavy mineral sands. The kind of dense, dark sands you might find deposited along ancient coastlines or riverbeds.
Okay.
Monazite is economically fascinating because it contains a healthy dose of light rare earths and, crucially, a much better percentage of some heavier elements compared to bastnäsite.
That sounds great.
It would be, but monazite carries a massive, literal toxic complication. It frequently contains high levels of thorium. Thorium is radioactive.
Yeah.
It sits right near uranium on the periodic table.
It is highly radioactive and naturally decays over time. If you decide to develop a monazite deposit, you are no longer just running a standard mining operation. You're suddenly thrust into the heavily regulated world of radioactive materials management.
Oh, man.
Yeah, the environmental permitting hurdles, the occupational safety protocols for dust inhalation, the specialized tailings facilities required to store radioactive waste safely for centuries. It radically alters the capital cost and timelines of the project. Many Western companies simply avoid monazite because the liability is too high.
Which leaves the third major profile, ion adsorption clays. And these seem to be the real geopolitical linchpin.
They absolutely are. These are not hard rocks that you have to blast with dynamite. These are literal clays formed over millions of years of heavy tropical weathering, predominantly in southern China and parts of Southeast Asia.
So the rock is already broken down.
The weathering process breaks down the original rock, and the rare earth ions are left simply clinging or adsorbed onto the surface of the clay particles.
So they aren't locked inside a tight crystalline prison. They're just clinging to the dirt.
Exactly. Because of that loose physical attachment, extracting them doesn't require crushing solid rock. You can chemically leach the rare earths out of the clay much more easily.
And what's the element breakdown like?
Here is the geopolitical kicker. These specific clays in southern China are uniquely, disproportionately rich in the heavy rare earths.
The dysprosium, the terbium.
The heat shields. China's historic stranglehold on heavy rare earths is intimately tied to the exploitation of these specific clay deposits.
But the environmental cost of that extraction has historically been devastating, hasn't it?
Devastating is the exact right word. Historically, operators would just pump harsh leaching acids directly into the hillsides.
Just right into the ground.
Right into the ground. The acid washes the rare earths out, but it also contaminates the groundwater, sterilizes the soil, and poisons the local watershed. China has cracked down on the worst of these illegal operations in recent years, but the legacy of environmental destruction is immense.
So mapping this out on a global scale, the data from our sources reveals a staggering picture of concentration. According to that Goldman Sachs analysis, China accounts for roughly 69% of global rare earth mining.
69% is a commanding majority, but if you look closely, mining is actually their weakest point of control in the entire supply chain.
Because the bottleneck tightens as you move downstream. I mean, the US and Australia mine the rock too, but as you move to the refining stage, China's market share jumps from 69% of mining to 92% of global refining.
92%.
When you get to the final step, the actual manufacturing of the magnets, China controls a jaw-dropping 98% of the market.
That progression, 69 to 92 to 98%, is the central thesis of modern resource geopolitics. China is not dominant simply because they were geologically blessed with the right dirt.
Right, because Australia has excellent dirt.
The U.S. has world-class dirt at Mountain Pass. China is dominant because, over the course of decades, they executed a patient, unified industrial strategy. They systematically built the mines, then they invested heavily in the chemical separation plants, then they built the metal-making facilities, and finally, the magnet manufacturing hubs.
They integrated the whole ecosystem.
Exactly. They built the entire complex industrial ecosystem.
Let's contrast that with the United States. According to the U.S. Geological Survey data for 2025 and 2026 provided in our sources, the U.S. actually mined an estimated 51,000 metric tons of rare earth mineral concentrate.
Mostly pulling from Mountain Pass in California.
Right, and if you just hear that number, 51,000 tons, it sounds like a booming self-sufficient domestic industry.
51,000 tons is a highly significant volume of raw material. Mountain Pass is a Tier 1 global asset.
But the very same USGS summary delivers this brutal reality check. In the exact same year we mined 51,000 tons of rock, the U.S. was 67% reliant on imports for rare earth compounds and metals. And for the heavy rare earths, the heat shields we absolutely must have, the U.S. import reliance was an astonishing 100%.
We mined the rock but remained totally strategically exposed.
Here's where it gets really interesting. The best way to visualize this contradiction is to think about agriculture. Imagine if the United States harvested tens of thousands of tons of the highest quality wheat in the world right here in the breadbasket. We have silos overflowing with wheat.
Okay.
But we don't own a single flour mill. And we don't own a single commercial oven. So what do? We scoop up all our freshly harvested grain, pack it onto massive cargo ships, and send it entirely overseas. A foreign country mills it into flour, bakes it into bread, and then we have to buy our own bread back from them at a massive premium, hoping they don't suddenly decide to cut off our food supply.
The agricultural analogy is perfect. America has the rock. We are producing the raw concentrate. But for a very long time, we completely lacked the sovereign industrial capacity, the mills and the ovens, to turn that dirt into the finished functional products we actually require.
Our sources do point to some other potential geological assets, right? Like Lynas, operating the massive Mount Weld mine in Australia, which is a crucial allied lifeline.
Yes.
And within the U.S., there are exploration projects like Round Top in Texas, which aims to provide a broader basket of elements, or Bear Lodge in Wyoming. There's even research into recovering rare earths from coal ash waste in Appalachia.
Those secondary sources and exploration projects are strategically vital to explore. But the text provides a stern warning. Geological options are not production.
Right, it's just potential.
A multi-element deposit like Round Top still has to prove its complex metallurgical flow sheets at scale. Finding trace amounts of rare earths in a mountain of coal waste is a great scientific proof of concept, but extracting it economically at a commercial scale, competing on price with Chinese operations, is a totally different universe. Resource potential does not equal secure supply.
Which brings up the most frustrating, obvious question. If we have the wheat, if we have 51,000 tons of concentrate sitting right there at Mountain Pass, why is it so incredibly hard to build the mills and the ovens? What exactly is the physical reality of turning this dusty rock into a shiny, high-performance permanent magnet?
To understand the difficulty, we have to walk through what the industry ominously calls the missing middle.
The missing middle.
The supply chain from rock to magnet is not a straight line where you just toss dirt into a furnace and metal comes out. It is a grueling, multi-stage gauntlet. At every single stage, the material physically changes form, the chemistry gets exponentially harder, the environmental hazards multiply, and the margin for error completely disappears.
Let's follow the journey of this material because the timeline our sources lay out is just intense. It begins with exploration drilling core samples to see if the rock is even worth mining. Then you hit permitting.
And permitting is not just a bureaucratic paperwork exercise. A rare earth mine is a massive physical intervention in the environment. You're dealing with complex water usage permits, air quality permits regarding dust, Endangered Species Act compliance, tribal and community consultations.
Plus, engineering those massive tailings ponds to safely store the waste rock and radioactive elements.
Exactly. In Western countries, this process alone routinely takes 5 to 10 years before a single shovel hits the dirt.
If you survive permitting, you move to construction building. The roads, the power grids, the water systems, the actual mine infrastructure.
Right.
Then comes the mining itself, blasting the hard rock with explosives, loading it into massive haul trucks, crushing it into gravel.
But you still don't have rare earth.
You just have crushed rock. You have to move to concentration.
Concentration uses physical and chemical methods like froth flotation to separate the rare earth-bearing minerals from the useless surrounding rock. And this is the stage where the U.S. produced its 51,000 tons. The output is a fine powder called a mineral concentrate.
But the concentrate is still basically just highly organized dirt. You can't put it in a motor.
It is entirely useless to a manufacturer. The rare earths are still locked tightly inside their crystalline mineral structures.
To break those structures, we move to the next brutal stage, cracking or digestion. You essentially bake the concentrate in massive kilns at extreme temperatures with highly corrosive acids like sulfuric or hydrochloric acid.
It's just an intense chemical reaction.
Very violent. It breaks the mineral bonds, dissolving the rare earths into a liquid solution. And this liquid solution finally feeds into the absolute beast of the entire supply chain, the heart of the bottleneck: separation.
Separation is where the geopolitical power of the 21st century truly resides. Because remember, our identical twins.
Holding hands.
The 17 elements are now floating together in an acidic soup. They are chemically almost indistinguishable. So how do you separate the neodymium you desperately need from the cerium you don't? It is a monumental chemical challenge.
How does it actually work on an industrial scale?
The dominant, commercially viable method used globally is called solvent extraction. I want you to imagine a sprawling, massive chemical plant filled with hundreds, sometimes thousands, of individual mixing tanks called mixer settlers. You take your acidic, water-based rare earth solution and pump it into a tank. Then you introduce a highly specialized organic solvent.
And what does the solvent do?
The organic solvent is engineered to have a very, very slight chemical preference for one specific rare earth element over the others based on microscopic differences in their ionic size. It acts like a chemical hook.
Okay, so it grabs the one you want.
You vigorously mix the water-based solution and the organic solvent together. The solvent grabs a tiny fraction of, say, the neodymium. Then you let the tank settle. Because water and organic solvents don't mix like oil and water, they separate into two distinct layers. You skim off the solvent layer, which now holds a slightly higher concentration of neodymium, and you pump it into the next tank to do it again.
But because their chemical preference is so slight, you can't just do this once and get pure neodymium.
Not even close. It is painstakingly inefficient. To get to the 99.9% purity required for advanced magnets, you have to repeat the separation process over and over and over again. The fluid cascades through hundreds or thousands of sequential stages in a continuous loop.
It literally sounds like trying to separate a cup of dissolved salt from a cup of dissolved sugar by using tweezers to pick out the molecules one by one.
On a molecular level, that is exactly what you are doing. It requires massive upfront capital to build the plant. It requires handling thousands of gallons of highly hazardous, flammable chemical reagents. It requires pristine, flawless waste management to ensure those acids and solvents don't leak into the groundwater.
Right.
But most importantly, and this is the absolute crux of why the West struggles to rebuild this, it requires an immense, deep well of localized know-how.
Know-how, meaning it's not just a blueprint you can download, it's institutional memory.
Exactly. You don't just finish building a solvent extraction plant, hit the on switch, and walk away. It is a living, breathing chemical beast. Operators have to learn exactly how their specific ore feedstock behaves, because every mine's rock is slightly different.
So they're constantly tweaking it.
Constantly. They have to manually tune the flow rates of the plant. They manage microscopic impurities that build up in the system. They have to keep recovery rates incredibly high while preventing the entire cascade of tanks from emulsifying and gumming up like a giant batch of ruined mayonnaise.
Oh man, a mayonnaise disaster.
Right. That kind of intuitive, hands-on chemical engineering knowledge cannot be bought instantly. It is accumulated through years and years of painful daily operation.
Okay, assuming you survive the nightmare of solvent extraction, your output is finally pure, separated elements, but they are in the form of oxides, a white powder of neodymium oxide. We still don't have a magnet. We have to move to metal making.
Oxides are chemically stable and happy. You have to force the oxygen away. You use intensive, high-temperature electrolytic reduction processes, passing massive amounts of electricity through molten salts to strip the oxygen away and force the powder into a pure, rare earth metal ingot.
And then allaying. You melt that pure neodymium metal together with iron, boron, and your dysprosium heat shields to create the exact chemical recipe for your magnet.
And finally, you arrive at magnet manufacturing. And again, I must stress, this is not a 19th century blacksmith pouring molten metal into a horseshoe mold. It is advanced precision materials engineering.
Walk me through how you actually make the physical magnet.
It is a process called powder metallurgy. First, you take that alloy ingot you just made and you crush it back down into an incredibly fine microscopic powder. Then you place that powder into a mold and expose it to a massive external electromagnetic field.
Why apply a magnetic field to the powder?
Because you need to force every single microscopic grain of that powder to physically rotate and align perfectly so their magnetic domains all point in the exact same direction.
Oh, wow.
Think of it like taking a deeply tangled, messy head of curly hair and combing it so every single strand lies perfectly flat and parallel. If the grains are misaligned, the final magnet will be weak.
Okay, so you align them.
Once they are aligned, you press the powder under extreme pressure to lock them in place. Then you sinter them, which means baking them at incredibly high heat just below their melting point so the particles fuse together. Finally, you machine the hard block into the precise shape your customer needs, and you have to coat it with nickel or epoxy because raw neodymium magnets will quickly oxidize and corrode into dust if exposed to the ambient air.
The level of precision is astounding. And you have to maintain insane quality control specifications at every single step because you aren't selling this to a toy maker. You are selling this to an aerospace defense contractor building a fighter jet or a major automaker who expects this motor to run flawlessly under immense stress for 20 years.
The qualification process alone, where the customer tests and approves your magnet for use in their product, can take several years. They require total traceability, zero defects, and absolute reliability.
So looking at this utterly insane gauntlet, the mining, the acids, the thousands of mixer settler tanks, the electrolysis, the microscopic alignment, the years of testing, I have to ask the question that I think a lot of our tech-minded listeners are yelling at their speakers right now.
Let's hear it.
If this missing middle, the separation, the metal making, the magnet manufacturing, is so incredibly profitable downstream and so strategically vital to national security, why doesn't a Silicon Valley billionaire or a massive U.S. auto company with deep pockets just take $1 billion, drive out to the Nevada desert tomorrow, and build a giant solvent extraction and magnet plant? Just throw massive amounts of cash at the problem and disrupt it.
Because you simply cannot treat heavy process engineering the way you treat software engineering. In Silicon Valley, the prevailing ethos is move fast and break things. You write code, you launch an app as a minimum viable product, and if it crashes, you patch the bugs later. The stakes are low.
Right, nobody gets hurt if a social media app goes down.
But if you try to move fast and break things in a solvent extraction plant, you don't get a bug report. You create a massive toxic chemical spill. You violently violate federal environmental laws. Your product is contaminated and rejected by the buyer, and you bankrupt your company overnight.
You can't just download chemical know-how from the cloud.
You really cannot. You can buy the stainless steel tanks and the piping, but you cannot instantly buy the years of operational tuning and human capital required to make that equipment run safely and profitably. You cannot bypass the strict regulatory years it takes to get environmental permits.
The automakers won't just trust you either, right?
Exactly. No amount of venture capital will force an automaker to put your unproven brand new magnet into their flagship $80,000 electric vehicle until you've run years of exhaustive physical reliability testing. Capital is necessary, but time and operational discipline are the true bottlenecks.
And this patient, methodical accumulation of time and discipline is exactly how China built its dominance. They didn't just dig the rock and export it. Over 30 years, they tolerated the massive environmental burdens that Western nations increasingly regulated away.
Yeah.
They integrated the chemical processing hubs directly adjacent to the mines. They linked that output to massive downstream manufacturing sectors, producing the consumer electronics and the EV motors domestically. The entire ecosystem became completely self-reinforcing.
A self-reinforcing industrial cluster. The immense processing capacity attracted global magnet customers who wanted cheap materials. The presence of those magnet customers justified building even more processing capacity. The chemical engineers learned by doing, optimizing the flow sheets year after year.
While the West just watched.
Western countries viewed rare earths simply as a minor commodity you could buy cheaply on an open, frictionless global market. China viewed them correctly as a sovereign industrial system that dictated downstream power.
And because they exert near total control over that system, they have the capability to weaponize it. Our sources point to some glaring historical examples of this leverage in action. Back in 2010, there was a fierce maritime dispute between China and Japan over the Senkaku-Diaoyu Islands.
Right, the fishing trawler incident.
Yeah, a Chinese fishing trawler collided with Japanese Coast Guard vessels. In the diplomatic fallout, Japan abruptly accused China of halting all rare earth exports to Japanese industry. The shock of that embargo, or even just the credible threat of losing supply, sent the Japanese automotive and electronics industries into an absolute panic. It forced Tokyo to radically change their industrial policy, desperately invest in Australian alternatives like Linus, and build up national stockpiles.
It was a wake-up call that the West largely hit the snooze button on. And we saw the exact same leverage deployed again just recently. The sources highlight that in April 2025, China tightened its export controls, specifically on the heavy rare earths, targeting terbium and dysprosium, the vital heat shields. They expanded those regulatory controls further in October 2025.
And what I found truly fascinating in the text is the observation that a complete 100% embargo isn't even necessary to cause chaos in Western supply chains.
It isn't. You don't need to completely shut off the tap to weaponize a highly complex supply chain. All you need is the subtle threat of a licensing delay.
Just a delay.
Yeah. If you are an aerospace manufacturer building jet engines or an automaker scaling EV production, you operate on incredibly tight, just-in-time manufacturing schedules. If your primary supplier calls and says, "We'd love to ship your dysprosium, but our government export license review might be delayed by 3 to 6 months for administrative reasons,"
Your entire assembly line freezes.
Exactly. You cannot build your aircraft. The uncertainty alone is enough to paralyze global industries and force major corporations to bend to political pressure behind closed doors.
Which leaves the U.S. and its allies completely exposed to that exact pressure. But, as we promised in the beginning of this deep dive, we aren't here just to admire the problem and panic. We are exposed, yes, but we are not entirely helpless. Which brings us to the American blueprint. How does the U.S. realistically go about rebuilding this shattered ecosystem?
We have to begin by taking a very cold, honest inventory of our actual strength and our glaring weaknesses. The U.S. does have foundational strengths. We have a Tier 1, world-class mine at Mountain Pass producing vast amounts of light, rare earth concentrate.
We've got the wheat.
We have the wheat. We possess massive domestic demand from both our immense defense sector and our advanced civilian manufacturing base. And, crucially, we have highly capable geopolitical allies, most notably Australia, with their established Linus operations, who are motivated to break the monopoly.
But the weaknesses are structural and severe. We have a near-total lack of heavy rare earth deposits within our own borders. We are completely missing the commercial solvent extraction separation capacity. We are largely missing the metal reduction and magnet manufacturing facilities, and perhaps the most difficult weakness to solve, because it is invisible. We have a fundamentally fragile commercial structure.
That commercial structure is the invisible trap that kills Western rare earth projects. It is a textbook example of a market failure. Let me paint a scenario. Let's say you are a procurement officer for a major civilian automaker in Detroit. Your mandate is to find the absolute cheapest, reliably high-quality motor magnet available so your company can keep the sticker price of its new EV competitive with foreign imports. If a subsidized foreign supplier offers you a qualified magnet for 20% less than a brand new, struggling American startup in Texas, what do?
You're bound by fiduciary duty to buy the cheaper magnet.
Right, because your job is the quarterly bottom line, not managing U.S. national security. The civilian market is ruthlessly optimized for the cheapest qualified part.
But the defense market, the Pentagon, operates on a completely different logic.
They need secure, resilient materials that absolutely will not be cut off during a geopolitical crisis or a shooting war. The fatal problem is that the national security premium, the extra cost required to build a cleaner, resilient domestic supply chain from scratch, is not priced into the private civilian transaction.
And the defense market alone just isn't big enough.
It simply isn't large enough in volume to sustain these massive billion-dollar chemical separation plants, and the civilian market refuses to pay the extra cost voluntarily.
So the free market on its own will never organically solve this vulnerability.
It will not. If you leave it entirely to the unguided free market, private companies will understandably hesitate to invest $1 billion into a domestic separation facility. They know that the moment their plant opens, state-subsidized foreign competitors can intentionally flood the market, temporarily crash global prices, bankrupt the American startup, and then simply raise prices again once the competition is dead.
Before we talk about how to fix that market failure, our sources do mention a couple of secondary scientific paths we can take to ease the supply pressure. Recycling is brought up frequently. The idea of recovering old magnets from dead computer hard drives, scrapped first-generation EVs, and decommissioned wind turbines.
Recycling is absolutely essential for the long-term sustainability of the industry. It bypasses the geological risk and the mining permitting entirely. You are mining the urban landscape,
Sounds ideal.
but it has severe volumetric limits in the near term. The massive wave of EVs and giant wind turbines being built today won't reach their end of life to be scrapped for another 10 to 20 years. Furthermore, extracting a tiny, glued-in, brittle, permanent magnet from a crushed mixed metal hard drive or a shredded EV motor is its own mechanical and chemical nightmare. You still have to process the recycled material chemically to purify it.
Another path mentioned is substitution, just engineering our way around the problem. The text specifically calls out Iron Magnetics, a fascinating company born out of University of Minnesota research, which is developing high-performance permanent magnets completely free of rare earths, utilizing abundant materials like iron nitride.
Substitution is vital, frontier research. If material scientists can invent a widely applicable permanent magnet that performs just as well without needing a single atom of neodymium or dysprosium, you instantly relieve a massive amount of strategic geopolitical pressure.
What substitution is not a magic wand.
No, engineers aren't going to lightly redesign an entire aerospace actuator or a finely tuned EV powertrain around an iron nitride magnet unless it flawlessly matches the exact magnetic strength, heat resistance, and physical durability of the incumbent rare earth version. It takes years, sometimes a decade, to fully qualify new substitute materials for mission-critical applications.
So while recycling and substitution are great long-term pressure valves, there's no avoiding the hard work. We have to build the missing middle. And the sources note we are finally seeing some concrete progress. The text highlights MPL Materials, the American company operating the Mountain Pass mine, building a massive new facility in Fort Worth, Texas. In 2025, they actually began commercial production of separated NdPr metal and initiated trial production of automotive-grade finished magnets, aiming for a 1,000 metric ton per year production wrap-up.
That facility represents exactly the right directional shift.
Yeah.
It takes the domestic rock from California, ships it to Texas, and connects it directly to domestic metal making and manufacturing. It proves the chemistry can be done here.
That's huge.
It is, but we have to be realistic about scale. A 1,000-ton plant, while a fantastic and necessary beachhead, is only a fraction of massive global demand. We need many more of those facilities, and we need them scaled up.
So what does this all mean? How does the U.S. actually formulate a grand strategy to fix this?
The sources distill a very specific layered strategy, and the absolute first conceptual hurdle we have to clear is accepting that autarky, meaning 100% total national independence, mining and refining every single element strictly inside the physical borders of the United States, is the wrong goal.
It's geologically and economically impossible.
It is impossible, and pursuing it would be economically ruinous. The realistic strategic goal should be removing single-point failure. We do not need to do everything ourselves. We just need to rigorously ensure that no single foreign rival holds a unilateral chokehold over any critical step in the chain.
The sources break this layered strategy down into actionable steps. Layer 1. Aggressively secure domestic light rare earth separation. Mountain Pass gives us the NdPr rock, the raw muscle. We absolutely must have the solvent extraction capacity to separate it locally.
Yes.
Layer 2. Realistically acknowledge our geological limits and source the heavy rare earths, the vital dysprosium and terbium heat shields, from trusted, stable allies like Australia because we just don't have the rich clay deposits domestically right now.
Layer 3 is aggressively building out the domestic metal and magnet manufacturing plants, replicating and scaling efforts like the Fort Worth facility so the separated material can actually be forged into a functional component.
And Layer 4.
Layer 4. This is the critical policy intervention using government procurement power to create artificial, stable demand.
Meaning the government steps in as the buyer of last resort to fix that market failure we talked about earlier.
Yes. Through sustained tax credits, long-term Department of Defense procurement contracts, or guaranteed price floor purchases, the government essentially signals to the private market. If you take the massive risk to build this domestic separation plant, we guarantee we will buy your magnets at a fair, sustainable price, even if a foreign rival temporarily crashes the global spot price to try and bankrupt you.
That removes the terrifying market risk.
It removes the market risk for private investors and keeps the nascent domestic ecosystem alive while it climbs the learning curve.
I really love the analogy the sources use to contextualize this at the end of the section. It argues that we need to view this industrial policy the same way we view basic national infrastructure. We don't wait for a literal shooting war to begin in the Pacific before we start drawing up blueprints and pouring steel for a new aircraft carrier.
No, that takes a decade.
And we don't wait for a catastrophic nationwide blackout to decide we should probably invest in maintaining the electric power grid. So why on earth should we wait for a catastrophic export ban to paralyze our economy before we decide to build a domestic magnet factory? It isn't a luxury item. It is fundamental infrastructure.
It is the hidden structural infrastructure that allows all visible technological power to function.
If we are going to treat this like building an aircraft carrier, if this is a massive generational national infrastructure project, we have to be honest about the timeline. Because you can't build an aircraft carrier or a solvent extraction plant in a weekend. Assuming we do everything right, when do we actually cross the finish line and get this resilient, secure supply chain?
The timeline is painfully long, it is rigidly fixed by the immutable laws of chemistry and heavy engineering, and it requires immense political patience. Based on the projections outlined in our sources, here is the realistic trajectory. By 2030, we can expect a significantly stronger light rare earth base.
So just 4 years out from the baseline data in our sources.
Yes. By 2030, the operations at Mountain Pass should be fully integrated downstream. Advanced facilities like the Fort Worth plant will be operating at a highly meaningful commercial scale. Early recycling streams will be coming online. We will have successfully insulated some of our most critical defense supply chains.
Okay.
But UT, and this is a massive caveat that policymakers must understand, full independence, especially concerning those irreplaceable heavy rare earths, is highly unlikely by 2030. The U.S. will still be strategically exposed.
Okay, so we push the horizon out to 2035.
2035 represents the first realistic window for a robust, resilient, fully allied supply chain. By then, we could finally possess a functioning, end-to-end mine-to-magnet alternative, distributed across the U.S., Australia, and other trusted partners capable of supplying our critical civilian and military applications completely free of Chinese influence.
And looking even further out to 2040 and beyond.
That is when you finally see a truly mature, stabilized system. The massive initial wave of EVs built in the 2020s will finally be retiring, providing a huge, steady stream of recycled magnet feedstock. New allied mines will have successfully navigated their agonizing, decade-long permitting and construction processes. But getting to that 2040 reality requires navigating an incredibly daunting obstacle course known as the risk stack.
The risk stack. This is the gauntlet of failure points that keeps mining CEOs awake at night. Let's run through it to truly appreciate the difficulty. First, geological risk. You spend millions of dollars drilling holes in the ground, and the rock just doesn't have the grade or the heavy rare earth percentage you modeled.
Followed immediately by metallurgical risk. You have the rock, but the specific crystal structure makes the chemistry required to extract the elements too complex or prohibitively expensive.
Environmental risk. Handling the toxic acids, the highly flammable solvents, and the radioactive thorium without causing an ecological disaster or getting shut down by regulators.
Permitting risk. The years, sometimes decades, spent in bureaucratic review, tribal consultations, or fighting endless litigation from local opposition groups who don't want to mine in their backyard.
Market risk. The absolute nightmare scenario, where you miraculously survive all of the above, you spend $1 billion building a pristine separation plant, and the very day you open, state-backed foreign competitors intentionally crash the global price of neodymium by 40%, bankrupting your operation instantly.
Followed by customer risk. You survive the price crash, but major automakers refuse to buy your magnet because they are terrified of tweaking their tightly qualified existing supply chains, or they decide to switch to an induction motor instead.
Geopolitical risk. Sudden export controls, punitive tariffs, trade wars, or outright embargoes that cut off your access to necessary chemical reagents or heavy rare earth feedstocks.
And finally, the most insidious of all, policy risk. The very real danger that the U.S. government gets highly alarmed during a brief geopolitical crisis, throws a massive influx of grant money at the problem, but then completely loses focus and pulls funding the moment the headlines fade and rare earths cycle out of the news.
That is a terrifying, compounding stack of risks.
Mhm.
But looking at that stack brings us to the ultimate synthesis of what this deep dive is really about. As our sources point out, we have spent decades cultivating this illusion of a weightless economy.
It is a profound, comforting illusion. We celebrate the sleek, aerodynamic design of a drone or the seamless touchscreen interface of a new electric vehicle, and we collectively pretend that the messy physical constraints of the 19th and 20th centuries no longer apply to us. But the brutal reality of rare earths proves that the physical world is still absolutely king.
A drone is not just a clever software algorithm. An EV is not just a digital app on wheels. A wind turbine is not just a manifestation of climate legislation.
They are massive, complex material systems. They are bound by the unforgiving laws of metallurgy, the stubbornness of chemistry, and the harsh realities of factory floor discipline. And the story of rare earths shows us exactly how a country like the United States can lead the entire world in pure invention designing the most advanced, breathtaking technology on Earth, while simultaneously remaining completely dependent on a strategic rival for the basic physical materials required to actually manufacture that invention.
It is the ultimate vulnerability of the pure optimization mindset. For decades, Western corporations optimized their operations purely for price. The only question asked in boardrooms was, where can I get this motor magnet the absolute cheapest? And by relentlessly doing that, they hid the immense strategic cost of that dependence in the invoice. The true, unavoidable cost of national resilience means accepting that the absolute cheapest global supply chain is no longer the safest one. We have to be willing to pay a physical and financial premium for security.
And that realization forces a very uncomfortable reckoning with our own environmental ideals. For a long, long time, the West has happily enjoyed the clean, finished, high-tech products of the rare earth industry, while quietly outsourcing all the toxic, radioactive, heavy industrial dirt to other countries. If we truly want a resilient, sovereign supply chain that we control, we can no longer wish the environmental footprint away to the developing world. We have to figure out how to reconcile strict environmental protection with heavy, dirty industrial capacity right here at home.
Which brings us right back to where we started this journey. We've taken you from the muddy, chemically stubborn banks of the geological lottery, where these elements are locked together in the dirt like identical twins. We've dragged you through the grueling, toxic gauntlet of solvent extraction, where millions of gallons of acids and chemicals are required to pry elements apart molecule by painstaking molecule. We've forged metals, aligned microscopic magnetic domains, and arrived at the stark, unbending geopolitical reality of modern physical power.
It is a physical reality that simply does not care about your software patents, your sleek marketing, or your legislative goals. It only cares about process engineering, long-term patient capital, and industrial endurance.
And so, we want to leave you with one final, slightly uncomfortable thought to mull over next time you're sitting in traffic. We all share this collective dream of a pristine, green, zero-emission future, driven by incredibly sleek electric vehicles and majestic, silent wind turbines dotting the horizon. But that pristine, clean future is entirely, fundamentally dependent on our willingness to master some of the dirtiest, most difficult, most hazardous industrial chemistry on Earth. Are we, as this society, finally willing to accept the physical and environmental footprint of our own progress right here in our own backyards? Or will we continue to outsource the dirt, and in doing so, risk losing the future entirely?
The power in the 21st century belongs to those who possess the grit to build the ovens, not just those who happen to harvest the wheat.
Thank you for joining us on this deep dive into the hidden material foundations of modern power. We hope you look at the sleek machines around you just a little bit differently from now on.